Right now, every system keeping you alive and connected depends on a single wire. When you wake up, your phone is charged, your water is pumped, the internet flickers to life. But behind the walls of your home is a fragile, massive grid that dictates how much our civilization can grow. For most of human history, creating power meant burning raw materials. Early steam engines allowed us to replace human and animal labor with mechanical force, but they required constant, heavy fuel. As factories scaled and mass production took over, our entire society became anchored to the continuous burning of coal and wood. We built an industrial world, but we locked ourselves into a system where progress was extremely expensive. To meet the exploding demand, we extracted oil and natural gas. These high-yield fuels built modern cities, but they are finite, difficult to extract, and dump vast amounts of emissions into the atmosphere. Today, 8 billion people share this planet. Every year, we need more electric vehicles, more cooling systems, and more factories. But producing the energy to run them remains destructive, costly, and strictly limited. We have reached a point where human progress is heavily capped. The barrier isn't a lack of ideas or intelligence. The barrier is that we cannot generate enough cheap power to build what we dream up. Scientists are attempting to remove this cap by perfecting nuclear fusion. They are building machines to replicate the specific physical process that powers the sun, right here on Earth. Instead of burning fossil fuels or splitting heavy uranium atoms, fusion reactors smash lightweight hydrogen atoms together. When they fuse, they release immense amounts of energy. There is no smoke, zero carbon emissions, and no mountains of long-term radioactive waste. This chart shows what happens to global markets when commercial fusion reactors come online. As global energy output skyrockets, the cost per kilowatt-hour crashes towards zero. If we map historical data for computing costs over the same graph, we see the same curve. Computers used to cost millions of dollars and required entire buildings. Now they are cheap enough to fit in your pocket. Electricity will follow that trajectory. When electricity becomes almost free, the basic math of human survival changes. We transition from a society defined by scarcity and the fight over finite resources into an economy driven by total abundance. Consider global water shortages. Earth actually has oceans full of water. The true issue is that we lack the cheap energy required to process it. Removing salt from seawater through desalination takes staggering amounts of electricity. But when that electricity costs a fraction of a cent, enormous desalination plants can run continuously along every coastline. Entire deserts can be irrigated and turned green. That same unlimited power moves agriculture indoors. Right now, farming is at the mercy of droughts, freezes, and massive transportation logistics. With zero-cost power, vertical farms can operate 24/7 inside major cities. We can grow fresh crops year-round in highly controlled climates, just kilometers away from the people who eat them. By neutralizing energy costs, humanity addresses its most pressing basic survival metrics, food and water. Both become abundant simultaneously. Beyond physical resources, nearly free electricity removes the ceiling on artificial intelligence.
The true bottleneck for modern AI isn't coding, but the massive electrical draw required to cool and operate data centers. Computation has always been hungry for power. From the earliest mid-century mainframes, calculating complex equations meant massive electric bills and limited running time. As the public internet expanded across the globe, server farms grew to handle the traffic, pulling entire percentages of the world's power supply just to route emails and host websites. If those energy costs drop to near zero, AI networks will run continuously at maximum capacity. Financial constraints will no longer throttle machine learning. This computational explosion accelerates downstream research. Medical institutions can simulate thousands of chemical compounds an hour to discover new drugs. Climate modeling, physics simulations, and material sciences advance rapidly. The speed of human innovation is directly tied to the budget of our compute. When that budget becomes infinite, our scientific output scales with it. Leaving Earth entirely is also an energy equation. Expanding into space requires immense thrust to escape gravity and intense continuous power to manufacture parts in orbit. When energy and manufacturing costs collapse, assembling large-scale infrastructure in orbit becomes a standard industrial practice. Orbital factories and heavy-duty lunar bases finally make economic sense. Sustaining human life on Mars requires generating massive amounts of heat, oxygen, and recycled water. A compact, nearly limitless fusion power source is exactly what makes permanent colonization possible. Abundant energy is the foundational requirement for humanity to graduate into a true Type 1 civilization. It is the factor that makes planetary expansion realistic. This engineering isn't theoretical. Right now, scientists at facilities like the National Ignition Facility in the US and the massive ITER project in France are actively constructing this infrastructure. These highly advanced prototypes are successfully containing superheated plasma, pushing us closer to commercial viability every year. But every massive leap in technology introduces severe risks. The immediate danger of abundant energy is deciding exactly who gets to control it. If electricity is practically free, corporations can automate entirely, eliminating millions of jobs overnight. Governments could run unlimited global surveillance networks without ever worrying about the operational cost. Fusion solved the mechanical equation for a thriving world, but it doesn't solve the human one. We will have to design the ethical frameworks to ensure that unlimited power actually benefits society rather than fracturing it. If you look back through history, progress isn't driven by consumer gadgets. It is driven by solving fundamental bottlenecks. Mastering fire gave us warmth. Harnessing electricity gave us modern cities. The internet gave us instant communication. Energy is the next major bottleneck. If your electricity bill disappeared tomorrow, and power was suddenly infinite, what would you build? How would your city change? Solving the energy problem provides the next generation the resources to build whatever future they can imagine. When we create abundance, we create opportunity.